Okay, so today we are starting with chemistry, and you will see that I gave you 4 booklets for chemistry. We have atoms, and then we have the periodic table. Then we also have chemical bonding and chemical change. Now, although there are 4 booklets, at least 3 of them sort of form a cohesive whole. So it's almost like puzzle pieces fitting together to give us a nice picture of what's going on in chemistry. So with that in mind, you will find that for the 3 videos about atoms, periodic table, and chemical bonding, the summaries that I'm going to do now, they will pretty much look the same. So the rest of the video will just be an application of that specific little booklet. All right, so let's just do a review of what we know about atoms. And to do that, I am going to use Olivia as our test subject. So during school camp, we turned oxygen into Olivia, which is a little monster because she is a non-metal. And just to recap that very quickly, the non-metals, hydrogen is sort of an odd one out, but all these on the right-hand side are your non-metals, your little monsters. And then everything here on the left-hand side are our metals, and our metals were our little gnomes. Now we also have the metalloids that are around the step, but I'm going to leave that for the periodic table video. So let's take oxygen and just redraw her information. Now, if we look at oxygen, we can see that she is in group 6. So we always look at the Roman numerals for the group. So she's in group 6 and she is in period 2. So I'm going to write a 2 there and a 6 there. Okay, so now we did this little summary in class as well, and you will remember different things at different times. It doesn't matter. I would really highly encourage you that when you get your exam paper, just after the 10 minutes reading time, that second that you can pick up your pen, is make this little summary so that you have something to reference back to. So with all these little numbers, we know a lot about oxygen, about Olivia. Now, the first one that I'm going to just make a note of, and then I'm going to ignore it, is this 3.8. So that 3.8 is the electronegativity of the element. And we have a definition for electronegativity, so that's one of the level 1 things that you have to just like memorize. Electronegativity, this is the ability of an atom to attract the electrons, making a bond it is involved in, and it increases across a period but decreases down a group. So for now, you can just make a mental note that it is the ability of an atom to attract the electrons in a bond. And when we get to chemical bonding, we will look at this value again. But for now, we are done with the 3.5. Let's look at the 8. Now, the 8 is very specific to Olivia. And when we go back to the periodic table, you will see that every one of the elements have their own unique number. So hydrogen is number 1, helium is number 2, lithium number 3, beryllium number 4, and all the way down. So if we look at Olivia or oxygen, oxygen has a number of 8. Okay, and that 8 tells us a lot of things. So firstly, it tells us the number of protons. Okay, and I'm going to draw a nice picture for you now. And if Olivia is in a neutral state, it also gives us the number of electrons. So it's always the number of protons, and most of the time, if oxygen is in a neutral state, it will also be the number of electrons. Now, the other number that goes with the 8 is the 6. So that's the group number. And the group number tells us something about the electrons that Olivia can play with. Okay, and that comes back to our Aufbau diagrams, the electron configuration diagrams that I'm going to draw next. Okay, so I'm going to say it's electrons, but I'm going to make a little star. So it's not the number of electrons, it's the number of electrons she has to play with. And in fancy words, it's called the valence electrons. Now, if you want a definition for valence electrons, it's not on the list that I gave you. But the valence electrons are the electrons located at the outermost shell of an atom, and that will become more clear when we do the electron configuration. The last number that I want to draw your attention to at the moment is the 2, and the 2 is the period that Olivia lives in. It is the row that she lives in, and this tells us how many shells. How many energy shells does she have? And when we were drawing the electron configuration diagrams, that was the number of stories that she has in her house, but we're going to draw that now. Okay, this 16 I am going to leave out for now, because this 16 we only use when we are working with stoichiometry, chemical change. So for now it is not important, so I'm not going to talk about the 16 at the moment. Okay, so if we look at oxygen, Olivia, there are 3 numbers that are important at the moment. We have the 8, that is the number of protons, and if it's a neutral atom, it is also the number of electrons. We have the 6, that is the group number, and that tells us the number of valence electrons, and those are the electrons in the outermost shell of an atom. And this number 2 tells us that these 6 electrons are located in shell number 2. But let's go draw Olivia and see what her electron configuration diagram or Aufbau diagram looks like. So we have our little gnome's nose, and in the gnome's nose I am going to write oxygen with a 0 in the air, and that 0 indicates that this is a neutral atom. So she still has all 8 her electrons. Then there, it looks like a hat to me. So these stories of the house is the energy shells. So we have 1 energy shell, and then 2 energy shells, 3 energy shells, and in school we go up to the 4th one. But for this one I'm going to stop at number 3, because I know oxygen only goes up to number 2. Okay, so in your first energy shell we only have 1 orbital, and that's your s orbital. So it's 1 little block, and inside that block we can fit in 2 electrons. But we will look at that now when we put the electrons in. In energy shell number 2, I have space for another 8 electrons. So first I have a s orbital where I can put in another 2, and then I have a p orbital where I can add another 6. Okay, so it's 1, 2, 3, 4, 5, 6, 7, 8. So I have a total of 8 electrons in my second shell, but I can only fit in 2 electrons in my first shell. Okay, so the first energy shell is sort of an odd one out. And then from here on up, it just repeats. So in the third energy shell, I will have 1 s and then 3 p blocks. Okay, so this is the general shape of the electron diagram, or the Aufbau diagram. Now there are 2 rules that I need to apply when I put those 8 electrons into the electron diagram. And I wonder if you can remember the names of the 2 people. So the one is Hund's rule, and the other one is Pauli's principle. Hund's rule is one of those things that you're going to learn. It says that electrons occupy equivalent orbitals, like the p orbitals in a shell, singly before pairing takes place. So if we look at this top one that we're not going to use because Olivia's electrons or gemstones don't go that high up. But Hund's rule says that if I want to put electrons in the p orbitals, I will not go 1, 2, 3, 4, 5, 6. Okay. We will first put 1 in the first block, and then 1 in another block, and then 1 in another block before I couple them with another electron. Okay, so Hund's rule says that if you see these as rooms, first you're going to put 1 person in every room, and then when there is 1 person in every room and I still have electrons to put in somewhere, then I can make couples. Okay, but Olivia doesn't go up all the way there. And then the other one is Pauli's principle, and Pauli's principle explains why when I put in the electrons, I make 1 arrow go up and 1 arrow come down. So Pauli's principle says each orbital may contain a maximum of 2 electrons spinning oppositely. So in every room, in every one of these blocks, I can only ever have 2 electrons, and when there are 2 electrons in one room, they need to have opposite spins. It just means that the one will spin in a clockwise direction and the other one will spin in the opposite direction. How they figure that out, I have no idea. It doesn't really have any bearing on anything else except the way that you complete the electron diagram. Okay, so now we are ready to put Olivia's gemstones into her house. We are ready to put oxygen's electrons into the Aufbau diagram. So we have a total of 8. So I'm going to start at 1s, and I'm going to do 1 and then 2. Okay, then I'm going to go 3 and 4. So you only ever do 1 level at a time. Okay, so we've got 4. Now I'm going to do 5, 6, 7. That is following Hund's rule. And then 8. And then I stop. Okay, because Olivia or oxygen only has 8 electrons. Okay, now let's look at energy shell number 2. So energy shell number 2 was that number 2. It's the period number. And we saw in our little summary that in energy shell number 2, I need to have 6 electrons. So let's test that. Here I have 1, 2, 3, 4, 5, 6. Okay, so the thing that I said is going to happen actually did happen. Now, Olivia is a little monster, so we used blue for her. So what I'm going to do is I'm going to color in the first energy shell in blue. Okay, now this is also supposed to be blue because she's a little monster. But this energy shell number 2 is special because this houses our valence electrons. And just to remind you the definition of valence electrons are the electrons located at the outermost shell of an atom. Okay, so at the moment we have a lot of information to our disposal, but it all comes from our periodic table. It's not really something that we necessarily have to remember, it's more understanding. Okay, so if we take oxygen, Olivia, as our example, from the periodic table we can see that she lives in row 2 and column 6. Or period 2 and group 6. Okay, so period and group are the fancy sciencey words, but if you just understand that I'm speaking about the row and the column, then that's fine too. So the row or the period that she's in tells us about the number of energy shells that she will occupy with her electrons. And the group number, the column number, tells us how many electrons will be in that outside energy shell. All right, and then the last number that we're working with now is the 8, and that tells us something about the number of protons, and if it's a neutral atom, the number of electrons as well. Now, while we're on this slide, I quickly want to draw oxygen in another way. Now, we just said that this 8 represents the number of protons and electrons. So what I'm going to do now is I'm going to take this gold color and I'm going to make 8 little dots, and those represent our protons. I'm just going to draw a little line around them, and that is to show you the nucleus. They're like the inside of the atom. Now, outside of this atom, I have energy shells, and those are the energy shells that I just drew you in the electron diagram. But if we draw it like we used to do it in grade 8 and in grade 9, I will have my first energy shell. That would be the blue one over there first. And that energy shell will have 2 electrons. I'm going to make them pink, and I'm putting them together so that we can actually visualize them. You might remember from last year, they would actually put them on opposite sides in the orbital. But I want to have this picture look a little bit more like the Aufbau diagram, so it's easier for you to comprehend what's going on at the moment. Then the next one, the next energy shell will be around that one, and in the outside energy shell, it's this green one, we have a total number of 6 electrons, and with these colorings that I used the silver. So we have 1 electron, so we need a total of 6, right? So there's 1, 2, 3, 4, 5, 6. And if you count all these little dots on the outside, you will find I have a total number of 8. And that is how I know this is Olivia, provided that this is a neutral atom. So this one is energy shell number 1. Energy shell number 1 will always only have 2 electrons. And this is energy shell number 2 that will always have space for 8. But in this case, it's only 6 electrons. Now this little inside, my nucleus at the moment contains 8 protons. And because it has 8 protons, I can identify this atom as an oxygen. Okay, so if you ever have to figure out the identity of an atom, always start with the nucleus, if you can see the nucleus, and count the number of protons. So the number of protons will always be the number in the periodic table. Now, we know that inside the nucleus, we have another set of particles. So we have our electrons, and those are negative, and those are the ones in the energy shells outside, and they move around. Then we have our protons. They are responsible for our positive charge. And then we have one more element. Those are our neutrons, and they just give us our mass. It gives the weight to the atom. And there can be different numbers of neutrons in your atom, and that is a number that they have to give you. You cannot find it on the periodic table. So for this example, I am going to put 5 neutrons in my nucleus. And now there's another way that we can represent all of this information in my little sketch. So we know now that inside the atom we have 8 protons, and that little number I'm going to write here at the bottom. And then I will have another number, which in this case would be a 13. And that 13 comes from the 8 protons plus my 5 neutrons. And this 13 number I call my mass number. So this mass number, this is a number that will have to be given to you. You cannot find it on the periodic table. The mass number tells you how many things are inside my nucleus. Okay, how many nucleoids do you have? So that's the fancy word. So I have 13 nucleoids, and because I know I'm working with Olivia, I know 8 of those are protons. So if I have 8 protons, then it means I need 5 neutrons to get to my mass number. So if you take the number of protons and you add the number of neutrons, you will get your mass number. Now, if I take Olivia that we just had with the 8 protons and the 5 neutrons, and I duplicate her, I clone her, she will look a little bit different. So she will still have 8 protons because she's still oxygen. But this isotope of oxygen might have 2 more neutrons. So let's just write this configuration again. So it is still oxygen. And we know it is oxygen because inside the nucleus I have 8 protons. But now if I count all the nucleoids, everything that's inside the nucleus, I have 5 protons, and in this case 7 neutrons, which now gives me a number of 15. So these 2 Olivias are twins, if you will. They are pretty much identical. The only thing that differs between the 2 is the number of neutrons that we have. And that's where the word isotope comes from. This is another definition that you can learn. So isotopes are atoms of the same element that contain the same number of protons but different number of neutrons, meaning they have the same atomic number but different mass numbers. So if you maybe want to add some more notes, if we look at this Olivia, then we know that 8 is the number of protons. And we also know that that number 8 tells us that she is number 8 in my periodic table. And that number we call the atomic number. So the atomic number is the number on the periodic table. You will always have that. The other number that we work with here is this 15. And this 15 we call the mass number. And that is the number of protons plus the number of neutrons. The mass number is not on the periodic table. It needs to be given to you. And if you understand what an isotope is, then it sort of makes sense. So all the information on the periodic table are averages. So they went out and they counted all the Olivias in the universe, and they found the average atomic mass. And that's where that 16 comes from. But for now, you don't have to know that. For now, you only have to know that every atom will have an atomic number that's on the periodic table, and it will have a mass number that they will have to give you. Now, there are little sums that we can do with isotopes, but I will do those when we get them in the questions. So for now, I just want you to know that there is something called an isotope, that there's a definition that you need to learn, and that this picture on the screen right now is a summary of what isotopes are. So if you just look quickly, these 2 atoms look identical. It's only when you zoom into the nucleus that you will find that although the number of protons are the same, because they are both oxygen, the number of neutrons are different. All right, so let's look at question 1. Now, I'm going to do the questions in this booklet a little bit differently than the way I did the physics. So the physics I did by reading through it, giving my brain some time to process the information, and then coming back and actually doing the sums. And the reason why I specifically did that is because there are sums, and sums are really heavy mind work, if you understand what I'm saying. With chemistry, as long as you have your summaries, as long as you have your little cheat sheets, then especially for the short form questions, you might be able to just answer the questions. Okay, so let's try another tactic and see if it works. I am going to just read through them first so I can figure out what's going on. So question 1 is true or false. Indicate whether the following statements are true or false. Now they give us information about neon, and they say that neon has 10 protons, 12 electrons, and 12 neutrons. Okay, so we'll figure that one out in a second. Atoms of elements are electrically neutral. The mass of an atom is equal to the mass of a neutron. The charge of all protons are the same. Every atom of nitrogen has 7 protons and 7 neutrons. The nucleus of an atom contains protons and neutrons. Atomic number of a substance tells us how many protons an element has. An atom on the whole has a positive charge. The maximum number of electrons in the first shell can be 8, and then the central part of an atom is called a nucleus. And what I'm going to try and do is I'm going to try to make a little summary here again, just in a shorter way. So if we look at question 1.1, they write neon in this way. And when they write neon in this way, it means that we are busy with this screen. Okay, so there's my little cheat sheet. And then I just want to go to the periodic table and just actually look at neon. So neon is over there. He or she is number 10. And because it's in column number 8, we know it's a noble gas. These are our noble sages. They do not want to give or take any electrons. They are very happy with who they are. Now, if we draw neon like this, we know neon is number 10, and number 10 is our atomic number, right? And that gives us the number of protons, and as long as it's a neutral element, it will also be the number of electrons. So they tell us that neon, each of these neons will have 10 protons, and that is true. Okay, so all neons in any place in the universe will always have 10 protons. So that is correct. Now the next one says that there are 12 electrons. Now normally we would want the protons and the electrons to be equal, because then we know we are working with a neutral element. And especially for group number 8, the noble gases, they will always exist as a neutral atom. Okay, so this number of electrons is false. Now they ask number 1.2, atoms of elements are electrically neutral. Now, when we were making the summary over here, I told you that we have 3 particles that make up an atom. We have electrons, and they are responsible for the negative charge. We have protons, they are responsible for the positive charge, and then we have neutrons that is responsible for the mass. Okay. Now, if we look at this atom, let's take this first Olivia, the inside, the nucleus, will have a positive charge of 8+, because she has 8 protons on the inside. If we look on the outside, she has 8 electrons. So the outside will have a charge of 8-. Okay, so the inside has a positive charge of 8+, the outside has a negative charge of 8-, and together they give us a neutral charge. That is why when we drew Olivia over here, we put the little 0 in the air to tell us that the charges basically cancels each other out. Okay, so if we come back to 1.2, atoms of an element are electrically neutral. That is true. So the inside is positive, the outside is negative, but if you look at the whole picture, it is electrically neutral. 1.3 tells us the mass of an electron is equal to the mass of a neutron, and that is false. That's just something that you can learn. 1.4, the charge of all protons are the same. That is true. They are all positive. Every proton in the whole universe, it doesn't matter where you find it, will always have a charge of +1. Now they ask us something about nitrogen. So if we come to our periodic table, nitrogen is over there. It's number 7. And if we draw nitrogen's information the same as what we did with neon, we see nitrogen is number 7 in the periodic table, and that means all nitrogens will always have 7 protons, and as long as it's neutral, it will have 7 electrons as well. And then they ask us something about the neutrons. Now remember, I told you, from the periodic table, we cannot say anything about the neutrons, these little red guys, because that is specific to every atom, and that's why we have isotopes. So every atom of nitrogen has 7 protons. That is correct. But every atom of nitrogen will not necessarily have 7 neutrons, for the same reason that every Olivia's neutrons won't be the same. So this Olivia had 5 neutrons and this Olivia had 7 neutrons. And if we draw another 5, they will all have different numbers. Or the same numbers, we do not know. Okay, so 1.5 is also false because we can't know that without looking at every single atom. 1.6, the nucleus of an atom contains protons and neutrons. So if we go back to our little sketch that we drew of the atom, then we know that is true. So on the inside the nucleus, we have the gold particles and the red particles. Your gold particles are your protons and the red ones are your neutrons. So there are protons in the nucleus and there are neutrons in the nucleus, so this is true. Number 1.7, the atomic number, that would be that 8, or in the case of neon, the 10. The atomic number of a substance tells us how many protons an element has, and that is true. An atom on the whole has a positive charge. Now, if you compare that with 1.2, you will see it's exactly the opposite statement. So atoms are electrically neutral, and we said that is true. An atom on the whole has a positive charge. That is false. And then 1.9, the maximum number of electrons in the first shell can be 8. And if we look at this one, it's not true. So all the other ones will have 8, but the first one is special. The first one can only hold 2 electrons. So this one is false. And then number 10, the central part of an atom is called a nucleus. That was that inside, and that is also true. So if we summarize everything that we just learned from question 1, we know that we can represent the atom like this. So on the inside, we have your nucleus, and that contains your protons and your neutrons. Okay, your protons is job. The proton's job is to give the atom or the nucleus a positive charge, and the job of the neutrons is to give it mass. Then on the outside, we have energy shells with electrons, and the job of the electrons is to give the whole atom a negative charge. And if we also look at this atom of Olivia, we see that the nucleus will have a total charge of 8 plus, because there are 8 protons. The outside will give me a charge of 8 negative, which means in a neutral atom, we will have a charge of 0. It will be electrically neutral. Okay, so that's all the information about an atom. And then we know there is something like isotopes, where they differ a little bit, and that is where this way of writing comes from. So the smallest number will always be your atomic number, and the symbol there is a Z. Okay, and then the bigger number that they have to give you is called your mass number, and that is a capital A. Okay, but you can just remember the smallest number will be the atomic number. That's the number of protons, and then the bigger one is your mass number. Then if we take neon as an example, inside the nucleus we will have protons and neutrons. And if we add them together, we will get our A number, our mass number. So the number of neutrons and your mass number needs to be given, and that is unique to every atom. Okay, question 2 is give one word for. 2.1 is the number of protons in the nucleus of an atom, which is characteristic of the chemical element and determines its place in the periodic table. So they're asking you, what do we call these little numbers? The 5, the 6, the 7, the 8. And if we go back to our little summary that we just made, it's that 10 that they're talking about, or that 8. And that is called our atomic number. So it's the number of the atom. Then they ask the collective name for the neutrons and the protons. So the neutrons and the protons, those are the things that are inside our nucleus. And when we put these elements together, we call them nucleons. I might have called them nucleoids earlier. Nucleoids is actually something about biology, but it tells you the same thing. It's the stuff that's inside the nucleus. So everything that's inside the nucleus, we call the nucleons. It sounds like something from Star Trek. Okay, 2.3, atoms having the same atomic number but different mass numbers. So we're coming back to this one again. So they have the same atomic numbers, but they have different mass numbers, and those are called isotopes. 2.4, element X has 8 electrons and 8 neutrons. So assuming that element X is in its neutral state, we can deduce that it will also have 8 protons. And 8 protons is the atomic number, so we can go find element X. Element X will be number 8 in my periodic table, and that is our dear Olivia. So this answer is oxygen. And then 2.5, the number associated with an element that represents the total number of protons and neutrons in a nucleus. So the number of protons and neutrons we just learned is nucleons. And we want to know, what do we call that special number? And if we just go back a second, we will see it's that capital A number, that is our mass number. Now, I'm not going to lie to you, I still get confused about the names for these different numbers. I understand what they are, but I get confused with the names. So what I do is I actually have a cheat sheet next to me so that I can remember to use the correct names. So the little number is your atomic number, that is your number of protons. The big number is your mass number. And the way I remember it is the two A's don't go together. So the atomic number can't be an A because the A's don't go together. That's a little rule I made up for myself. So the atomic number must be the Z then. I would just go and make a little cheat sheet and rewrite it a couple of times until you can remember it. Now for question 3, the multiple choice questions. So the first one, they give us magnesium. And if we look at the second one, sodium, and they are giving us the mass numbers and the atomic numbers. So we are back to this little summary of ours. So let's just go look at Maggie. Our Maggie is number 12 here on the periodic table. So we know that magnesium has 12 protons. So if we write Maggie in that form, I know the bottom number will be a 12, and that is our number of protons. And then this other number, which will be the 24, will be our mass number. And that is equal to the protons plus the neutrons. Okay, so if I have 12 protons, it means in this case I also have 12 neutrons, because 12 and 12 makes 24. They are asking us for the number of neutrons, and that is what I determined just there. So almost in the same way that I did the kinematics and the electric circuits, I sort of ignored the question and just went out and figured out, what do I know about Maggie? And then I went back to the question to figure out what they actually want me to answer. So the number of neutrons is 12. The answer there is D. If we look at the second one, that is sodium, and sodium is number 11 on the periodic table. So if we do the same little summary, there's sodium, is number 11. So there's sodium, the little one there is 11. And if we look at what they gave us, this top number is 23. So we know there are 11 protons, which means if I do a little sum, this will be 12 neutrons, right? Because 11 plus 12 gives me 23. So they're asking again for the number of neutrons, and that will be the 12 again. Okay. 3.3. When atom X of an element in group 1 ionizes to become X plus, what happens? Okay, so this one is a little bit involved just because the options that they give us is a little bit obscure. Now, they tell us we are working with X, an element in group 1. Now, that's very impersonal. So let's go find someone. Let's take Lily. We like Lily. So if we look at Lily, Lily is number 3 in the periodic table. And we know we can draw Lily with 3 electrons. I'm just going to use round electrons and not the stripes because I just want to get my head around what's going on. So if I look at Lily just in her neutral state, I know she has 3 protons and 3 electrons, and I don't have enough information to make a call about the neutrons. So we don't know anything about the neutrons. All right. So this is Lily with a 0 charge. Now we can change Lily into Lily 1 plus. So that valence electron there at the outside, remember the valence electrons are the electrons that she can play with. Okay, so that valence electron she can give away to someone because she's a metal. And then her electron diagram will look like this. So she will only have 2 electrons in the first shell and nothing in the second shell, and that will cause her to have a charge of +1. All right, now the last thing I want to show you here is if I write it in this way. So we know she has 3 protons, and then let's make her mass number a 5. Okay, so the mass number is everything that's inside the nucleus, and that will never change. Okay, for this lily will always have 5 nucleons. This lily will look exactly the same. So she might have lost or given away one of her electrons, but the stuff inside her hasn't changed. So now we test the statements. A tells us the mass number of X increases. Now the mass number is this number, and it hasn't changed. Okay, so if the mass number changes, it means I'm working with another lily or another lithium. So that's false. The atomic number of X decreases. Now the atomic number is this little 3 that tells me I'm working with Lily, and it is that 3 and it is that 3. That 3 will never change for Lily or for lithium, because if it changes, then I'm not working with Lily anymore. If we look at number C, the charge of the nucleus increases, and that sort of goes with B. So the charge of the nucleus increases implies that we have more or less protons. And that is not possible, because if the number of protons changes, then the atomic number changes, which means it's not lithium anymore. So the only one that's left is D. The number of occupied energy levels decreases, and I sort of showed it there. So if we look at the neutral lithium, she occupies energy level 1 and energy level 2. But when she gives one of her electrons, the valence electron, away, energy shell number 2 suddenly is empty. So lithium 1+ only goes up to the first energy level. So 3.3's answer is D. This one was quite involved. I would have left that one to right at the end because I had to really think hard about what I know. 3.4. Each of the substances below is formed by attractive forces between ions. In which one of the substances do the constituent ions have the same electron configuration? Okay, now this is one that's going to take me a while because I need to go and draw the electron configuration for each of these elements. I'm not going to do it right now. I'll come back to 3.4. If we look at 3.5, they tell us the numbers 11 and 23 are associated with sodium. Which one of the following is correct? Now, let's just go back one. We actually have sodium. Sodium is there. So they're talking about the numbers 11 and 23, and with our little summary about sodium, we see there's the 11 and there is the 23. If we look at 11, 11 is this top number, that is our atomic number, and we know that is the number of protons. Okay, it's what I wrote there, and it's been in our summary all along. Now the other number will always be your number of nucleons. So that's your protons plus your neutrons. Okay. So this 23 that's on the periodic table, that's like the average of all the sodium atoms that they went to measure. But if we look at an individual sodium atom, it might not be 23. Okay. So if we know that we have 11 protons and we have a total of 23 nucleons, then it means that our number of neutrons, just like we had in this example, will be 12. Okay, and now we just test what we know. So they tell us there are 23 protons, that's not true. We have 12 neutrons, that is correct. We have 11 neutrons, that is false. We have 11 protons. And then 12 nucleons. Nucleons, remember, is the collective name for protons and neutrons, so that one is also false. Okay, so you really need to know the names of these numbers to get these types of questions correct. 3.6 tells us which atom in the ground state, meaning it's neutral, has only 3 electrons in its 3p suborbital. Now, for this one, I would actually just go and draw my little gnome. So it's someone, I'm not sure who that is at the moment. So they're talking about the 3p suborbital. So I have 1, 2, 3 energy levels. And then I add my orbitals. So the single one is S and the 3 together is our P. And now they tell us we have 3 electrons in the 3p orbitals. So there's 1, 2, 3. So if I have 3 there, it means all the rest are occupied. Because Hund's rule tells us that we do one level at a time from the bottom up. So if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I am looking for element number 15. And if I come to my periodic table, number 15 will be P, and P is phosphorus. So at first, when I read this, I had no cooking clue how to do that. But I know how to draw my little gnome, and I know how to put the jewels into the rooms. So that is what I did. And by drawing it, and because I like drawing my little gnome with the rooms and the jewels, it sort of calmed me down. Okay, so that X I can now substitute with a P and a P. Which atom in the ground state, so it's neutral again, consists of a partially filled 3p orbital? So this one is just to show you the different words that they can use to ask the same question. Okay, so they can either tell you there are 3 electrons in the 3p sub-level, or they can just tell you that it is partially filled. That 3p also tells me that it is someone in the 3rd row. So if we look at argon, potassium, calcium, and aluminium, these are the 4 options that we have for an answer. Okay, now if we look at the question, just again, the partially filled 3p orbital tells me that it is in row 3. So immediately I can ignore calcium and potassium, because calcium and potassium are both in row 4. We want someone that is in row 3, and there we have an option of aluminum and argon. And if you go draw aluminum, you will see she will have a partially filled 3p orbital, where argon will be fully filled, because that is the definition of a noble gas. All the noble gases will have a fully filled energy level. So I encourage you to go and draw aluminum so that you can see what went on there. So the answer here is D. 3.8, the number of electrons in an atom of element X is 15, so that's the electrons. The number of neutrons is 16. Which of the following is a correct representation of an atom of this element? So let's just draw it on our own. So we have X. Now again, assuming that it is a neutral atom, the number of electrons will equal the number of protons. So our little number over there is 15. And if we have 16 neutrons, we know that if we add the protons plus the neutrons, that will give us our mass number. That is our big Z. The protons, we just figured out, is 15. And the neutrons are 16. So that gives me a number of 31. So this is the way that I will write it. And now, after I've written it, now I'm going to look for my answer. And the answer is A. Okay, so don't first look at the options. It's just going to confuse you. First take what you do know on your own and figure out the answer, and then come and look for your answer. Okay, so now we can look at the long form questions, and you will see it will just be repetition of what we've already done. With question 4, they give us the 3 isotopes of carbon. So we know it's carbon because we have the letter C there, and then we have the 12, the 13, and the 14. Now, if we look at carbon, carbon is over there. So we know carbon has 6 protons, and all these other numbers that they give us will be our mass numbers. So another way of drawing that first isotope will be C6, that is carbon, and then a 12 in the air. So that 12 will be the protons plus the neutrons. And then the second one will be 6 and 13, and the last one will be 6 and 14. So if we look at the first one, we know there are 6 protons, and because that number is 12, I will have 6 neutrons. For the second one, I will have 6 protons, because it's carbon, and I will have 7 neutrons in this case. And then for the last one, 6 protons and 8 neutrons. So this is everything that I know about these carbons. So let's answer the questions. 4.1, the element is carbon, because it's a C. The number 6 refers to the, you can write the atomic number, or you can say the number of protons. Both will be correct. The numbers 12, 13, and 14 refer to the what? So those are the big numbers. Those are our mass numbers. It will also be the number of nucleons. How many protons and neutrons are in the first isotope? Now you see I already wrote it down. I'm just copying my answers now. So I have 6 protons and 6 neutrons, and that is where that 12 comes from. For the second isotope, I have 6 protons and 7 neutrons. That is how I get to the 13. And for the last one, it is 6 protons plus 8 neutrons, and that is how I got to the 14. Okay, so just more of the same stuff that we did in the short form questions. Okay, question 5. Consider the diagram below showing 3 different neutral atoms A, B, and C. And then they're asking us a bunch of stuff. So let's just go look at A, B, and C. Let's start with the crosses on the outside. So here you can see this is energy level number 1. And I have 2 electrons there. And then I have energy level number 2. And I have 1, 2, 3, 4 electrons there. So for this element A, I can see that I have 6 electrons. And because they are neutral, I also know that I will have 6 protons. Okay. For the second one, I have 1, 2, 3, 4, 5, 6 again. So 6 electrons, those are my crosses, and therefore 6 protons because it's neutral. And then for the last one, I have 1, 2, 3, 4, 5. So I have 5 electrons and 5 protons. Now, since I know the number of protons, I can go to my periodic table and just actually get their identities. I don't know if it's going to be asked, but since I can determine it, why not? So we're looking for number 5 and number 6. There is number 5, boron, and number 6 is carbon. So this will be carbon and boron. Okay, let's go look at the questions. What is the name given to the collection of particles at the center of an atom? Can you remember? It's your nucleons. It does sound like something from Star Trek. What are the particles represented by the crosses? Those are your electrons. Which 2 atoms are isotopes of the same element? Give a reason for your answer. Now, the 2 atoms that are isotopes of each other would be A and B. And we know it is A and B because they have the same number of protons. And then the reason that you will give there will just be the definition of an isotope. Which element does atom A represent? Now, we already did that. A would be carbon for 2 marks. And then which type of particle in an atom has a negative charge? That comes from our little summary. That will be your electrons. And then explain what occurs when an atom becomes a negative ion. So we actually don't have an example of that. And to give you an example of that, I am going to use Claudine. If we look at the periodic table and we come and look for Claudine, we can see that she has 17 electrons. So let's put them in. So it's 1, 2. I'm making dots just because of space problems, but you can use your arrows. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So the way that it is drawn now, this is chlorine with a 0 charge. But when she becomes a negative ion, and because she's a little monster, remember she wants to receive something more, we're going to add 1 more electron. And now she has a filled energy state, which means that she will look like argon now. And that is the whole reasoning behind why atoms on the periodic table either lose electrons or gain electrons. It's because they want to become the noble gases, your noble sages. And you can come and explain this in any way that you feel comfortable with, as long as you tell me that she received or take up an electron. And the reason why she does that is so that she can look like a noble gas. Question 6 we did do in class, and I am going to skip this one just for a second and come back to it when we're done. So I'm going to use question 6 just to make sure that we understand everything that we are learning with these long form questions. If we look at question 7, they tell us that we have an electron diagram configuration of a neutral atom. Okay, so that is important. And then they ask us a couple of questions. Now, let's just stop for a second before we look at the questions and just figure out who this is. All right. So each of these little arrows represents an electron. And because it's a neutral atom, our number of protons will be the same as the number of our electrons. So if we count these electrons, we have 16 electrons. And number 16 on our periodic table is sulfur. So this electron diagram in question 7 represents sulfur. So let's just quickly draw sulfur. So 16 is our number of protons, and because it's neutral, it is also our number of electrons. And then 32 is our molar mass. That is something that we use with the calculations that we're doing in another video. All right, let's look at the questions. What name is given to this type of diagram? So this is our electron configuration diagram. Name the element represented by this electron configuration. So that would be sulfur. Write the electron configuration of this element in the SP notation. So now they're just asking us, this is very bulky and it takes up a lot of space. Is there a way that we can write it shorter? Now they ask us, state the group and the period in the periodic table to which this element belongs. Now if we just quickly go back to the periodic table and look at sulfur, sulfur is in row 3 and in column 6. So she's in row 3 and in column 6, but these numbers I could actually get from the electron configuration as well, remember, because this 3 tells me the highest energy shell that is occupied. So the highest number that I have is 3. And this 6 tells me how many electrons are in the outside energy shell. And there I have 1, 2, 3, 4, 5, 6. So I didn't need to go to the periodic table, but since I will always have a periodic table with me, there's nothing wrong with going there first. Now they're asking justify the answer to the previous question and then state whether the element is a metal or a non-metal. So let's start from the bottom up just because we can. So if we look at our periodic table and we know our step is here somewhere, we know everything to the right, we colored in blue, those are our little monsters, and those are our non-metals. Sulfur is a non-metal. Okay, what is the name of this type of diagram? So it's the electron configuration diagram, just like we had on our poster. Name the element represented by this electron configuration, so that is sulfur. Write the electron configuration of this element in the SP notation. So what we're going to do now is we're just going to write this shorthand. So we write 1s, that's our first orbital, and we have 2 electrons in the first orbital. My next orbital is the 2s orbital, and in that orbital I have 2 electrons. The next orbital is my 2p orbital, and I can count the electrons, there are 6 of them. Then I have 3s2 and 3p4. So this is the electron configuration. Now, just to remind you a little bit about what we learned here, we have energy shells on the inside, and the electrons that are housed there will always stay with the atom. They will never be shared. Okay, but the electrons in the outer shell, those are our valence electrons, they will be shared. And you can actually see that in the SP notation. So the outside energy shell, which I made green, those are the ones that she can play with. These are your valence electrons, and that's the number 6 that we had there. And then all the other electrons are the electrons inside the inner shells of the atom, and those will not be shared. Now, if we look at this blue part, you will see that I have a total of 10 electrons. Okay, so let's just go to our periodic table and see which one of our noble gases has 10 electrons, and that would be neon. So an even shorter way of writing this would be to take all these inside electrons and change them into the noble gas that they represent, that is neon, and all the electrons that are in the outer energy shell, the valence electrons, I write. Okay, so both of these are correct. The bottom one will be the normal SP notation, and then the top one will be the shortened SP notation. Okay, so 7.3 I've done. Now they ask state the group and period on the periodic table to which this element belongs. And now, assuming that I didn't have my periodic table, I will be able to read this off of my electron diagram. So the group is the 6, and the period is the 3. Okay, and I see it here as well. So the highest number that I have, that will be my period, because that is the same as my energy shell. And the number of electrons inside that shell will represent my group. Now with 7.5, they just want you to explain how you got to the answer. So you can say that the highest energy level, which is 3, is represented by the period number, and then the number of electrons in the energy level, which will be our 6, represents the group. Okay, and then 7.6 we've already done. Okay, so for this question, it counts 11 marks, and I have about 13 minutes to fill this in. I've been busy for about 9 minutes now, and the reason why I can do it faster than 13 minutes is, again, because I did an information dump first. First, I started from what do I know? And then I sort of played with puzzle pieces until I could answer all the questions. Now, for question 8 is just more practice in drawing the electron diagram, writing the long form of the electron configuration, and then the short form. And then they ask, chlorine will receive an electron to become an ion. Draw the electron diagram of chlorine. Now write the long form and then write the short form again. So it is just the same thing. And we basically did it during camp. So if you have your poster in front of you, we did chlorine and we did magnesium as well. So if you understand and you can remember what we did in camp, you can just skip over this question. If you need a refresher, you can maybe listen to this on double speed. All right, let's start with chlorine, and we are first doing the neutral atom. And if I look on my periodic table, chlorine is number 17 on the periodic table. So she has 17 gemstones, jewels, that she can put in her little house. Let's draw the house. Now, if we just look at the periodic table for a second, there is chlorine. Chlorine is in period 3 and in group 7. So this 3 tells me that she will have 3 stories in her house. So we will start with story 1. So energy level number 1 only has 1 orbital, and that's the s orbital. And then we have energy shell number 2, where we have an s orbital and a p orbital, and then energy shell number 3 will also have an s1 and a p1. Okay, let's do the joules, the electrons, and we're following Hund's rule and Pauli's principle. So Hund's rule says that we do one level at a time. Pauli's principle says that they have opposite spins, and I can only ever put 2 electrons into a little box. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. Okay, so this is the electron configuration diagram. If I have to write this in the SP notation, then they just want me to take this picture and turn it into words. And I'm going to write it up here. So we have the 1 s orbital, this is the bottom one over there, and we have 2 electrons over there. Then I have the 2 s orbital, there's 2 over there. And then I've got the 2 p orbital, there's 6 over there. Then the 3s, I have 2 in that one, and then the last one is 3p, and here I have 1, 2, 3, 4, 5 electrons. So to use the coloring that I used earlier, these in the outside energy shell, those are our valence electrons. These on the inside are the electrons that she won't give away. They will always stay with her. Now again, just like earlier, these inside electrons will always correspond to a noble gas. And we have 10 electrons again, which means we're working with neon. So for chlorine, we can write this even shorter. We can say, well, it's neon, and then we add the valence electrons. And since we're busy, let's just add some color. So these are the inside electrons. They will never be shared. And then the outside layer, that is where our valence electrons are. Those are the electrons that she can play with. And because Claudine is a little monster, she wants to receive more electrons. Let's quickly draw her. So if we look at Claudine and we say, well, she actually wants one more electron, okay, because all atoms always want a full energy level. So for Claudine, it's easier to just go and find one extra electron than to go through all that trouble of losing the 7 that she already has. Okay, so if we add one more electron, it means that Claudine now does not have 17 electrons. She now has 18 electrons. And because we added one electron, her charge will be -1. All right. So we have to change the short form and the long form electron configurations, the way we write them. So right now, she has 2 electrons in the 3s orbital, and she has another 6 in the p orbital. And that means that she now has a filled energy shell, which is exactly what she wants. And now she looks like argon, okay, because argon has 18 electrons. So the short form, it will just be to say that now she looks like argon. So now she is a noble sage. And that is why atoms of the nonmetals will always receive electrons so that they can become the noble sage right in front of them. Okay, so I have answered all the questions about Claudine. So we have the electron diagram. This is your picture. Now, I know this is a gnome, and we don't really want gnomes in science. So what you're going to do is you can draw this in pencil. And what you're going to do then, you're just going to take out all the fairy tale elements and just tidy it up a little bit. So let's just write it seriously. So there's our 1s orbital. Then we have the 2s and 2p, and then we'll have a 3s and a 3p. We put them nice on top of each other. The p orbitals have 3 blocks. And there. And then I'm going to add the electrons just the way I said. This is really not very neat. Please do it better. But this is your electron diagram, just like we had in this example. Okay, so draw the fairy tale one in pencil, and then just with your pen write over that and make it nice and neat, and you will get all your marks. The next one we're looking at is magnesium, dear Maggie, and Maggie is there. She's number 12 in our periodic table. Now Maggie is a metal, so I am going to use yellow. So Maggie, first we're looking at the neutral atom, and if we look at the neutral atom, she will have 12 electrons. Let's first just put them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so from this drawing, I can see that she will be in row 3 and in column 2. So if we just go back to our periodic table, is that really where we find her? Row 3, column 2? Okay, so the row 3, column 2, and that's exactly where Maggie is. Okay, so you can either start from the periodic table and then double check yourself, or start with the electron diagram and then double check yourself. So it's a good idea just to make sure that your 2 pictures are actually talking to each other. Let's write the short form. So the single blocks are your s orbitals, and the 3 blocks are your p orbitals. So it's 1s2, 2s2, 2p6, and then 3s2. Okay, so it's exactly what I drew here. Now I'm just writing it in a shorter form. If we look at the inner electrons, those will be all the electrons in the first 2 energy shells. Those are the electrons that she will never give away. She needs those for her own survival. But then in the outside energy shell, she has her valence electrons, and those are the ones that she can play with. All right, so she can either give them away or take some more in. But because she is a little gnome, we know that she will prefer to give them away. So for her, it's easier to give 2 electrons away so that she can end up with a filled energy level 2 than to go find 6 more. Okay, so it's always about the shortest path to get to where you want to be. So if we look again at the short form, we again start with neon, because neon is the noble gas with 10 electrons. So the yellow part I can swap with neon, and then I just say, well, she's still got 2 valence electrons to work with. If we look at the iron that will form, we know that she is going to give away her valence electrons, which means that she will end up with a charge of 2+. So initially she had 2 electrons in the 3s orbital. Those were her valence electrons, but now she will give those away, which means in the long form electron configuration, she will take those out. It also means that she doesn't have 12 electrons anymore, she only has 10. And because she only has 10 electrons, she looks now exactly like neon. So she has become the noble sage closest to her. All right, so if we just look at the periodic table again, all your non-metals will find an electron somewhere to become the next noble gas, where with your metal atoms, they will lose electrons to become the previous noble gas. These two slides you can use to fill in the electron configuration diagrams that are on your poster if you do not have them yet. The other positive atom that we worked with was Lily, so you can also add Lily there. And then the other negative one we had was oxygen. So this is oxygen when she is neutral, but you can add the other 2 electrons to make her negative in exactly the same way we just did with Claudine. Now question 9 I like a lot because it makes doubly sure that you actually understand what's going on here. Now I hope by this point in the video you have noticed that although it is a lot of different pieces of information, they do sort of form a whole. Okay, so we have an SP notation of 2 elements, P and Q, and they are given there. And then they ask us a couple of questions. Now before I'm going to worry about the questions, I'm going to redraw it. Now, if you prefer redrawing it, that is awesome. It's going to take a little bit of time, but just like with the circuits, we know that if we just go and draw it very quickly, it doesn't have to be neat. It actually makes us a little bit faster. So if we look at P, I have 1s2, so I have 2 electrons there, and then 2s2, so another 2 electrons, and then I have 4 electrons in the p orbital. So I have 1, 2, 3, 4. Let's just add my subscripts. That's S, S, and P. I have a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons. So I'm looking for number 8 on my periodic table. And if I go to my periodic table and I look for number 8, it is dear Olivia again. So there I can put an O, and there I can put an O and an O. Okay, so that was P, and now I'm going to do the same for Q. Now Q goes up to the 3rd energy level. So we have 2 electrons in the 2s orbital, and then another 2 in the 2s, 6 in the p orbital, 1, 2, 3, 4, 5, 6, and then 2 in the 3s orbital, and then 5 in the next one. 1, 2, 3, 4, 5. Okay, if I count all of these electrons, I get a total of 17. So I'm looking for element number 17 on the periodic table, and if you do not know that yet, it is Claudine or chlorine. Okay, so this is again the electron diagram of the neutral chlorine atom. Before we look at the questions, let's just write some notes. So if we look at chlorine, we know that she is in row 3, the fancy word is period, and she has 7 electrons, valence electrons, so she is in group 7. If we look at oxygen, oxygen will be in row 2 or period 2, and she has 6 valence electrons, so she's in group 6. Okay, so 9.1 they ask, give us the name or symbol of P, and we already determined that she's oxygen or just O, and then Q will be either Cl or chlorine. Refer to the periodic table and write down the following. Okay, now we can go back to the periodic table, but we also have all the information in a little sketch. So what is the number of the group to which Q belongs? Q is chlorine, and the group number we said is 7. What is the period to which P belongs? So P is up here, this is oxygen, and the period we said is 2. Is element P a metal or a non-metal? So P was oxygen, so she's a non-metal because she's on the right side of the step in the periodic table. Give the valency of Q. So the valency of Q, now Q was chlorine. Now the valency here will be 1. Okay, only 1, not -1. So valency is related to the valence electrons, but it tells us what does chlorine need to form a bond. So those electrons that are involved in forming a bond, how many of those are there? And there's 1. So chlorine needs 1 electron, and then she will be able to form a bond. And that's also where the charge of -1 comes from if we look at this. So that -1 is related to the valency, but the valency is just 1. There's no sign. It's a little bit confusing, I know. 9.7 asks the name of the chemical bond that forms when P and Q react. So P and Q are both little monsters, and when monsters bond together, we have a covalent bond. And we will look at the bonds in the bonding video. And then the last one is what type of compound is formed, right? Either ionic or covalent. And we sort of answered that. It's covalent. Now, question 10, 11, and 12 is all about isotopes that we haven't really looked at yet in terms of sums. So just to remind you about the isotopes, isotopes are 2 atoms of the same element that with just a quick glance, they look exactly the same. They will have the same number of electrons and the same number of protons, the gold particles, but they won't have the same number of neutrons, the red ones. So question 10 is an application of exactly that. Right, they say, you look up a particle substance in the periodic table and you find the following. Okay, so let's just write that down. So we have chlorine again. 17 and 35. We know the 17 is the number of protons, and as long as it's a neutral atom, it will also be the number of electrons. And we know that this 35 is made up by protons and neutrons. And since we know the protons are 17, I got it there, it means that the number of neutrons will be 18. Those are protons, our gold numbers, and then these are our neutrons, our red ones. Mr. Jobs says that he can easily prepare this element in the fume cupboard in his lab. However, when he prepares the substance, he says he will produce chlorine 35 and chlorine 37. Okay? Bearing in mind that Mr. Job is a highly respected, competent magician and can do all sorts of tricks, do you believe that this will happen? So it's a yes/no answer. Yes, it's possible. And we know it's possible because of this picture. Okay. We used oxygen as an example, and we saw that oxygen can have different number of neutrons in the nucleus. So if it's possible for oxygen, it's possible for chlorine as well. Write down what the numbers represent and all the things that we can deduce from the representation. There are at least 6 different things that we can deduce from this. Whoa. Now 6 different things at first seems a lot, but not really, because I just did chlorine 35 and I already have 3 things to say. So we know that the first one has 17 protons and 18 neutrons because the mass number is 35. And then for the second one, it will have 17 protons, 20 neutrons, and we know that because the mass number is given as 37. And that's pretty much it, and it just comes from our little cheat sheet that we've been using. 10.3 asks us, what is the name given to 35.5? Now, the 35.5 is not going to make any sense unless you come to the periodic table. So if you come to the periodic table, I don't know if you can see that. So chlorine has a 17 at the top and a 35.5 at the bottom. So 17 is our atomic number. And the word that we use for 35 is our molar mass. And molar mass is the word that we use when we are busy with stoichiometry. But when we are solely looking at the atoms, it has another name. And then we call it the relative atomic mass. And just to put that into perspective, we know that this 35 is called our mass number. So does it make sense that I can also call it the atomic mass? But this is the atomic mass of this specific chlorine atom. All right, but now we know we have a gazillion chlorine atoms out there and they each have their own unique mass numbers. But we can't have so many numbers floating around. So what they did is they determined the average of all those mass numbers. And that is how we got to the relative atomic mass. So they basically just took all the individual mass numbers and they found the average. So for 10.4, you're just going to say it's the average of the mass numbers of all the isotopes. Question 11. Iodine is an element that exists as two isotopes, of which one is iodine 53131. Okay, so if my mass number is 131 and I know I have 53 protons, then I know the other number that I'm looking for is 78. And then they explain how we use iodine to kill cancer. 11.1 asks what are isotopes of an element. So they're just asking you for the definition of an isotope, and we have that. Isotopes are atoms of the same element that contain the same number of protons but different numbers of neutrons, meaning they have the same atomic number, that is the 53, but different mass numbers, that is the 131. How many protons and neutrons does the above isotope contain? I've already done that. So it's 53 protons and 78 neutrons. Another isotope of iodine has 75 neutrons. Represent this isotope using the same notation as above. So I've got it here. I only need to change the 78 into a 75. And then obviously change the 131. So I'm going to take that out and that out. This becomes 75. And then I get a value of 128. Now, this is my short form little summary of what I wrote. But to get all my marks, I need to take this out. They don't want that. Okay. But I'm going to leave it in for now. What you also can do is do this in pencil and then just rewrite this part in pen. And then erase the rest. Do you think the isotopes of iodine will have similar chemical properties? Provide a reason for your answer. Now, when we look at chemical properties, we're not really writing about that in this exam, but the chemical properties are all dependent on the valence electrons. So if we look at group 7, to which iodine belongs, you will see that there are other atoms that will also have a valency of 1. Or 7 electrons in the outside energy shell, which means that all these halogens, those are the ones called in group 7, all the halogens will have the same chemical properties. So if you know chlorine really well, then you will also know bromine and iodine and fluorine. They won't be exactly the same, but they will be similar. Now the question at 11.4 is, do you think isotopes of iodine will have similar chemical properties? The answer is exactly the same. So all the isotopes of iodine will stay in group 7. And because they stay in group 7, they will all have a valency of 1, and therefore their chemical properties will be almost identical. Question 12. Now we are doing the isotope sums. Now we are just doing the sums. So this is more math than science, really. It also helps us to organize all the information more in a table form, but I'm going to start with my little sketch because that keeps me safe. Question 12 says, complete the following table by writing the question numbers in your answer book. Write the appropriate answer next to each question. You do not need to redraw the table. Okay, so they just want the answers. So we're working with magnesium, sodium, and chlorine. Now we actually know magnesium. She's number 12. Sodium is number 11 and chlorine is number 17. And if you can't remember that, you're just going to go back to your periodic table and find them. So there's magnesium, there's sodium, and there's chlorine. And we are only interested in the atomic numbers, the top numbers. Okay. So we also know that we have like a template for how we write these things. So we have a small number at the bottom usually, and then the big number at the top. The small number is our atomic number, and that is the same as our protons. And then the bigger number is our mass number, and that is our protons plus our neutrons. Now remember, the number of neutrons we cannot find on the periodic table, so they need to give that to us. Now to take magnesium, sodium, and chlorine and just write it sort of in the right way, I'm just going to move their atomic numbers down, and then let's see what else they give us. So let's look at magnesium. So this is the magnesium atom. We have magnesium. They tell us the Z number is 12, and I know the Z number is 12 because that comes from our periodic table. they're asking for the number of electrons. Now, because this is an atom, we know that the protons will be the same as the electrons, and in this case it will be 12. Okay, so here we can add a 12. Now they also tell us that we have 12 neutrons, which means if I take my 12 protons and I add my 12 neutrons, I get a number of 24. So because this bigger number is 24, I can write it over there. So exactly what we did here with iodine, we are now doing with magnesium. If you want to add the colors again, 12 are our protons, and then red is our neutrons. And when you write it, you're not going to write this, that you're going to take out. You're only going to write the 24, the 12, and the Mg. Now for sodium, they asked the sodium ion. Now I get that the ion makes things change, but let's just start with the atom first and figure out what's going on there. So we already know that sodium has 11 protons, and together with the protons we will have neutrons, which they don't give us, and the protons and the neutrons together will give me my mass number, which they give us is 23. So if those are my protons, then it means I need another 12 to get to 23. So 12 are the number of neutrons. So we can write a 12 over there. And now they're also asking for the number of electrons. Now the sodium ion will have 11 electrons, but because sodium is in group 1, and sodium really wants to look like neon rather, sodium will give away one of its electrons to become neon. So the number of electrons here will only be 10. Okay, sodium will give one away. If we do the same for chlorine, so they're asking for the Z number. Now the Z number is the number of protons, and that will always be the same. It's the same as our atomic number, that's 17. They give us the bigger number, 36. Now we know that 36 is made up of the protons plus the neutrons. And this, I think, will be 16. So 17 is the number of protons. That is our Z number. And then the protons plus the neutrons will give me, that is not right. Okay, this should be 19. Please use your calculator and not your head, because you make silly mistakes. So the number of neutrons we can just come and add here is 19. Okay, and then we have it all. Also, they speak about the chlorine atom again. So the number of electrons makes sense. She hasn't received another electron yet to form a bond. Question 12.1 asks or tells us naturally occurring chlorine consists of 76% chlorine 35 and 24% chlorine 37. Show, using a suitable calculation, that the relative atomic mass, so that's that bottom number in the periodic table, right, is 35.48. And for this we have a little formula. You're going to learn the formula and just use it the way we use all the other formulas. This formula won't be given to you though. So your relative atomic mass we write as AR. So the relative atomic mass. And the formula works like this. You're going to take the percentage and times it with your mass number. And then you're going to take the other percentage and multiply that with your mass number. And you keep going until you've used all your percentages. And then at the bottom, you're going to add all the percentages together. The bottom will obviously be 100. But if they give it in parts or in fractions, then this formula will also work. Okay, so this is our formula. Now we're just going to substitute. So we have 76 times 35. That's that first pair of information. And then we have 24 times 37. And we divide it by 76 plus 24. And it's a good idea to write it like this, because then you can just double check that you actually have 100%. And now it's just putting it into your calculator. And then I do get a number of 35.48. Okay, and there we are done. So you will probably get a mark for the formula and then a mark for the two substitutions. You can't get a mark here for the answer because they give you the answer. And then 12.2, what is the name given to the two forms of the same element, such as chlorine 35 and chlorine 37? And for 2 marks, you can tell them it is isotopes. So question 13 is another isotope sum. So if you are unsure about the isotope sums and you just want to go through one or two more examples with me, then you can watch question 13. So you will see for this sum, it's 3 marks, which means I have 3.5 minutes to do this sum. Now I'm actually going to time us and see how long it takes. So reading, naturally occurring europium consists of 2 isotopes with a mass of 151 and 153. Europium 151 has an abundance of that percentage, and europium 153 has an abundance of that. What is the atomic mass of europium? And I'm not going to be lazy and cheat and copy the formula. I'm actually going to write it. So the relative atomic mass is my percentage times my mass number. And I only have 2 percentages. And then I'm adding my percentages. So it is 151 times 48.03 plus 153 times 51.97. And then I add my percentages, so 48.03 plus 51.97. And I put this into my calculator exactly like it is there. And then I get an answer of 152.04 if I round to 2 decimals. And the time now is 010000. So it has taken me 2 minutes to do this sum. And this really should go as fast as this, because there's a formula that you're going to learn. You're going to parrot it until you remember it. You're going to write it down. You're going to do the substitution, put it in your calculator, and write the answer. So there's really no reason why you should get this wrong or why it should take any longer than 2 minutes. So titanium is going to be a little bit more work, because now we have 5 isotopes. So we've got that isotope, this one, this one, this one, and this one. Okay, now you can pause the video, write it out. It might take a little bit longer than 2 minutes because we have more numbers to work with, but the idea is exactly the same. Now I'm showing my substitution. So the first percentage is 8. I'm not going to put in the 0.0. And the mass number is 46. And then we have 47. 48, 49, and 50. Okay, now there are lots of numbers, so just do the calculator work nice and slowly and make sure you don't make any typos. And now I get a number of 47.92 if I round to 2 decimals. And that is my answer. One way of maybe just double checking yourself is this number that you get must be more or less the same as the number on the periodic table. Titanium is over there. So the relative atomic mass is 48. And with my sum, I just determined that it's 47.9. So if I round, I actually get to that number. So as long as there's not something wrong with the sum, you should get the number on the periodic table. Okay, question 14 is a mixture of questions. They talk about things there, but it's about chlorine again. They've asked to find the term isotope, we've had that, and explain why the 2 cylinders have unequal mass. Now you actually need to read the question. So grade 10 learners are working with 2 identical cylinders having the same volume of chlorine gas. However, they found that the mass of the 2 cylinders is not equal. The teacher says it's because they are isotopes. And we know what the definition of isotope is. We just wrote it. So the reason why they have unequal mass is because the mass numbers of the isotopes differ. So if you look at the nucleus of each of these atoms, they won't have the same mass. So they're just basically asking you to apply the definition of isotope in a way that makes sense. Now they give us the isotopes of chlorine again. So it's the same 2 we had earlier. And then they're asking us for this isotope, which number represents the mass number. Now this should just come very easily. It is the 35. The bigger number is your mass number. Which isotope has the most neutrons in its nucleus? So we know they each have 17 protons, which means the isotope with 37 nucleons will be the isotope with the most neutrons. You can do a little sum if you want to prove that to yourself. Then they ask Pauli's exclusion principle, that's your definition, and then write down the SP notation for chlorine. Now, depending on how relaxed you feel about the SP notation and the electron diagrams, the electron configuration diagrams, you can either do it just by writing it, or you can first go draw it. So in the beginning, and because I like drawing the gnomes in anyway, I would first draw chlorine, and we've actually had her. So you can first draw her and then write the SP notation. The other option is just to write the SP notation. So we know we have one s orbital and there's space for 2. Then we have a 2s orbital, there's space for another 2. Then we have the 2p orbital, there's space for 6. And then 3s2, 3p6. I'm just going to write it 4s2. So this is the generic one, but I only want 17 electrons. So over there I have 10, and then I need another 7. I've got 1, 2 plus 6, that's 8. So that must change into a 5. So find a way that's comfortable for you. Like I said, for me, I would actually just quickly go draw chlorine and then write the SP notation. And then just to remind you, we can write it in a shorter way, where we take the inner electrons and just change it into neon. And then write the valence electrons that are left over. They're not asking for the short form, but they're not specifying either, so both of these will be correct. Question 15, and then we are done. Chlorine is a non-metallic element with an atomic number of 17 and can exist as isotopes. Define the term atomic number and isotopes. So the definition of atomic number is the number of protons in the nucleus of an atom, which is characteristic of the chemical element and determines its place in the periodic table. But if you just write is the number of protons and it gives us the place in the periodic table, then that'll be awesome. And then isotopes we've had. Then they ask us, natural chlorine consists of chlorine 35 and chlorine 37. Write down the SP notation of chlorine again. Okay, we've done that. I'm not going to do that again. And then the relative atomic mass of chlorine is 35. Calculate the percentage of chlorine 35 in natural chlorine. Now this question, the math is a little bit involved. I'm going to show you how to do it. And it should sort of make sense if you see what I'm going to do next. But don't worry too much about this. These type of questions I think are more applicable to grade 11 and 12. Okay, so now you will find that I want to do my sum with isotopes, and I know I have a formula. So I wrote the formula even though I don't know yet how to apply the information. Now the problem I'm coming up to is I don't have any percentages. In all the other sums that I did, I had percentages to work with, but now I don't have them. And whenever that happens in science, we are going to make stuff up, but not completely. We're going to work with X. So just to explain to you with numbers first, let's say I have 10% of this chlorine. Does it make sense I would have 90% of the other one? Okay. Now for the same reasoning, if I had X% of the first isotope, does it make sense that I will have 100 minus X% for the other one? Okay, so we know there's 100%. It will always be 100. If the one is 10%, the other one needs to be 90% because we need to end up with 100. And in the same way, you determine the 90 with the 10, you can determine the 100 minus X with the X. Okay, so it's a little bit of a shock to the system if you've never done a sum like this before, but it works exactly like the numbers. And now you have everything that you need. So they tell us the relative atomic mass of chlorine is 35. So we actually have the answer. That's 35.5. Then my first percentage is now X, and my mass number is 35. And my other percentage in a bracket is 100 minus X, and my mass number is 37. And I still divide it by 100. Okay, so this is the science. Now we are going to tackle the math. So first things first, I want to get rid of the fraction. So I'm going to times the 100 to the other side. So then I get 3550 equals. There are brackets. I don't like brackets. I'm going to get rid of them. So X times 35 is just 35X. And then I have 100 times 37. So that is 3700, and then I have minus x times 37, which becomes minus 37x. Okay, now it's a normal linear equation. I'm going to move the 3700, and I'm going to keep the x's together. Then I am simplifying with my calculator. I get a value of minus 150, and on the right hand side I get minus 2x, and if I divide, I get x equals 75. So chlorine 35 accounts for 75% of the isotopes, where chlorine 37 will account for the rest, which is 25%. So the moral of this question is just to show you that even if you don't know exactly how to answer the question, if it is about isotopes, just write down the formula for isotopes and do any substitution that you possibly can. And if they don't give you percentages, you're going to have to make up your own percentages by using x. Now, the only question I think that I haven't done is question 3.4, and it is going to take quite a while because you need to draw the electron configuration of all these. Now, it's a very good practice one to do. So if you have time, draw the electron configuration of potassium, but remember now it's the potassium ion, right? And the bromine ion, and the same for sodium and sulfur. So it's sodium 1 plus and sulfur 2 minus. Draw them and just compare the electron configurations. So draw the little electron configurations, draw the gnomes and see which ones look the same.